Hello and welcome. We're constantly bombarded by health news, right? One day coffee is good for you, the next it's bad. It's a lot of noise. But what if you had a framework to find the real signal in all of that? Well, today we're going to build that framework. We're going to use the tools of epidemiology to understand how scientists really separate fact from fiction. Okay, let's dive into this.
So we'll start with a classic headline grabber. For decades, studies have gone back and forth on this question. Is our daily cup of coffee secretly harming our hearts? As you're about to see, the simple yes or no that you read in the headline is almost never the full story. This question is going to be our guide as we learn to think like an epidemiologist.
You see, to get to the truth, researchers have to navigate three huge, fundamental challenges. Think of this as our roadmap for the journey. First, they have to deal with the interference, all these outside factors that can create totally false associations. Second, they have to ensure the calibration of their tools is perfect, that they're actually measuring what they think they're measuring. And finally, and this is a big one, all of this has to happen within the boundary, those unyielding ethical rules that govern any research on human beings.
Okay, let's tackle that first challenge, interference. This is where so many of those misleading headlines are born. It's all about unmasking hidden variables that create what we call an illusion of cause, a situation where two things look connected, but the link isn't actually direct at all.
Now check this out, because this right here, this basically solves our whole coffee mystery. In those early studies, it really did look like drinking coffee was linked to heart disease. But this diagram reveals the illusion. The real villain? It was a third variable, tobacco use. You see, it turned out that heavy coffee drinkers were often also smokers, so tobacco is a true risk factor for heart disease, and it's also associated with the exposure, in this case coffee. This creates a confused, or as we say, a confounded and false association, making it seem like there's a direct line between coffee and heart disease when there isn't one.
So let's put a formal name to this idea. It's called confounding, and the term actually comes from the Latin confundere, which literally means to mix together. And that's a perfect description of what's happening. The effect of smoking is getting all mixed in with the effect of coffee, completely distorting the truth and creating a ton of confusion.
So how do scientists untangle this kind of mess? Well, thankfully, they have a really powerful toolkit. This matrix shows off some of the key methods. For example, in the design phase, before they even collect a single piece of data, they can use something like restriction. Maybe they decide to only study non-smokers. That way, tobacco is removed from the equation entirely. Or later, in the analysis phase, once all the data is collected, they can use fancy statistical modeling to mathematically adjust for the influence of smoking. It's all about filtering out that noise to find the real signal.
Okay, so we've dealt with the outside interference. We filtered the noise, but our work isn't done yet. Now we have to look inward at the research tools themselves. Are they properly calibrated? How do we really know our measurements are hitting the mark?
And this is a brilliant way to illustrate the two key concepts here: reliability, which is all about precision, and validity, which is all about truth. So look at that target on the bottom right. All the shots are clustered tightly together. That's high reliability. You can repeat it, but they're way off the bullseye, so it's low validity. It's not true. The goal is always that top right target, a tight cluster sitting right on the bullseye. You need high reliability and high validity. A study is really only useful if it's both.
And this idea of validity, it gets even deeper, because there are two crucial levels. First, a study has to have what we call internal validity. This just means the results have to be correct for the specific group of people being studied. It's the absolute foundation. Only after you've established that can you even start to ask about external validity, which is whether these results can be generalized to other people in other places. You got to get it right for your own group first before you can even think about claiming it's a universal truth.
All right, we've filtered the noise, we've calibrated our instruments, but we can't forget the most important element of all, the source of all our data: people. And this brings us to our third and final pillar, the ethical guardrails that absolutely must surround all scientific research.
When you're doing research with people, there are 4 unbreakable rules. These are the pillars that hold up the entire structure. First, informed consent. Participants have to know exactly what they're signing up for and be free to leave anytime. Second, confidentiality. Their personal data has to be protected, period. Third, human rights. The interests of the group can never just erase the rights of the individual. And fourth, scientific integrity. The research itself has to be honest and totally transparent.
And believe me, the need for these rules is not theoretical. Just look at this tragic case file. In an effort to stop cholera in Bangladesh, millions of tube wells were installed to provide clean groundwater. It was a well-intentioned action, for sure,
But the oversight, it was catastrophic. No one tested the water for naturally occurring heavy metals. And the result? A slow-motion poisoning of an entire population, with around 30 million people now exposed to dangerously high levels of arsenic. It's a hard lesson. Good intentions are no substitute for ethical monitoring.
Sometimes these ethical questions involve a really difficult balance. This slide shows that tension perfectly, the seesaw between protecting the health of the group versus the rights of the individual. In Cuba, a super aggressive program of testing and isolating infected individuals was, very successful at containing the spread of HIV/AIDS. But that public health victory came at the direct expense of individual liberty. The key takeaway here is that public health efforts are rarely successful in the long run without rock-solid guarantees that individual rights will be protected.
So, we've walked through the 3 core challenges: avoiding interference, calibrating our instruments, and honoring our ethical boundaries. Now, let's bring it all together. You can really think of the entire process as a single, powerful formula, the epidemiologist's equation.
And here it is. This is the formula for finding the real signal. You take a rigorous methodology, that's controlling for confounding, and you add precision measurement, that's ensuring validity, and together, that equals scientific truth. But look closely, the entire thing is surrounded by those ethical guardrails. Why? Because a valid result that was obtained unethically? Well, that's not legitimate science. Both pieces of this puzzle are absolutely essential to the mandate of public health.
So now you have the blueprint. You know to ask, could there be a confounder at play here? Is the measurement valid? And was this research even conducted ethically? The next time you see one of those confusing health headlines, you'll be equipped not just to read it, but to actually analyze it. You'll be ready to seek the signal.